In the 1940s and 50s, the most advanced machines on the planet could calculate artillery trajectories in seconds, but they were totally blind. To harness that power, humans had to learn to speak the machine's language. Back then, computing was a physical, tedious process known as cafeteria-style computing. You didn't type on a screen. You translated your commands by punching precise rectangular holes into stiff paper cards, feeding them into a reader, and hoping for the best. After handing over a stack of those cards, a programmer might wait hours or even days for a printed response. If there was a single syntax error, a hole punched a millimeter too far to the left, the entire process had to start over. The immense processing power of early digital logic was trapped. It was severely bottlenecked by the slow physical communication barrier. The solution predated the computer. In 1897, Carl Ferdinand Braun invented the cathode ray tube, or CRT. This vacuum tube oscilloscope used an electron gun and fluorescent screen purely to visualize analog voltage data as glowing wave patterns on a dark glass vase. It wasn't until the 1950s that military systems like SAGE adapted this tube technology. They took Braun's oscilloscope and used it to visually represent digital data to human operators in real time. This adaptation forged the first cognitive bridge between human and machine. Abstract digital logic was translated into visible, instantly readable metaphors. To understand these screens, look at the CRT cross-section. An electron gun fires high-speed beams, sweeping across a phosphor-coated interior to illuminate dots. This generates X-ray radiation. To protect the user, manufacturers built the tubes using extremely thick, heavy leaded glass to block those rays. The internal chemistry was just as hazardous. Early models relied on toxic heavy metals, like cadmium, to make the red phosphors glow, long before rare earth metals replaced them. Despite the toxic materials and massive weight, these glowing monitors enabled the graphical user interface revolution. By the 1970s, systems like the Xerox Alto were showing us the office system of tomorrow. As personal computers exploded in popularity, people accepted this trade-off. They placed these massive, deep display units, like this Apple II setup, onto everyday office desks. The CRT made visual computing possible, but its reliance on heavy, toxic materials created a physical and environmental footprint that couldn't scale forever. By the early 2000s, offices were facing a space crisis. A standard beige CRT consumed over 40 centimeters of desk depth. Workspaces were shrinking, and the monitor was taking up half the desk. The challenger was the liquid crystal display, or LCD. It offered an incredibly thin, flat profile that instantly freed up physical space. It wasn't a perfect replacement right away. Early LCDs actually suffered from motion ghosting, where fast-moving images leave a blur, and they had poor viewing angles compared to the older CRTs. Look at this exploded view of an LCD. Instead of a vacuum tube, it uses a backlight passing through polarizing filters and a layer of liquid crystals, controlled by a transparent conductor called indium tin oxide. It completely eliminated the need for lead glass and bulky electron guns. The LCD didn't conquer the market by offering better initial image quality. It won because it solved the physical constraints of the desk, and in doing so, it directly enabled the invention of the laptop. Today, the monitor has evolved from a simple output device into the primary engine of an $80 billion global economy. That demand surged recently with the shift to remote work and hybrid offices. Professionals are investing heavily in setups like this one, allowing them to juggle video conferencing on one screen while analyzing data on another. We're seeing a parallel explosion in the esports and gaming sectors. Competitive play requires massive, specialized displays with ultra-high refresh rates, driving a completely different segment of hardware engineering. There are distinct regional nuances too. In India, the market is dominated by 1080p IPS panels. IPS stands for in-plane switching, a display technology that provides a perfect balance of affordability and high color accuracy for growing professional sectors. Modern digital labor and entertainment now rest entirely on this visual infrastructure, cementing the monitor as a primary economic tool. But this massive global market has hidden vulnerabilities. It relies on highly fragile supply chains and is constantly threatened by global shortages of semiconductors and display components. There is also a growing environmental toll. As consumers rapidly upgrade to larger and faster screens, the volume of electronic waste continues to mount. To keep pushing forward, the industry is looking to innovations like micro-LEDs, AI-integrated smart monitors, and transparent screens that blend seamlessly into our environments. We are moving far away from the heavy, toxic past of the CRT. Today, manufacturers are shifting towards self-emissive organic light-emitting diodes, or OLEDs, and pushing for sustainable, circular manufacturing to reclaim rare earth elements. Over the last century, the monitor has completed its evolution. The display has transitioned from a hazardous laboratory instrument into a pervasive visual skin, acting as the interface where human perception finally meets digital logic.